Hi there, welcome back. I'm still on the Grundig 3160. I'm working on the cabinet. It's proving quite a lot tougher than I thought, but I'll be getting back to that as soon as I get some progress to report. But in the meantime, I've had a few questions about the switching on this particular system and in general on these German radio systems, and they tend to draw them following the same convention. So I decided to do a little exercise here and try with the help of some graphics to make this a little bit more understandable. And this is the best way that I've found for me to understand it. And if you can get some insight out of it as well, great. So this is what we have. This is the switching arrangement that we have on the radio. It's not particularly clear, so I decided to clear it up. And this is the result. So what do we have here exactly? Well, we've got basically three switching systems on here. We've got the one on the left. This is on the bass treble switch. We've got the main switch assembly, which is all the keys that select the various functions. And we've got the jazz and orchestra switch on the right here. You've got the keys on the top here, and you're looking at this from the underside. And what it says here is that it's drawn in the off position. Now, the way this particular radio works is you select any of those, pickup, long wave, medium wave, short wave, or FM, and it switches the radio on. Any one of those switches it on. And then you hit this off button and it switches it off. So everything snaps back. Whichever one has been selected, which has activated the on, snaps back when you push off. So in the off position, it cuts off the power because it has a toggle switch, but it also activates a switch over here, which is F and G. Now, what exactly does it do? Well, in the off position, this is where it is. So F and G are shorted. And whenever you activate any of the others, this thing breaks. In other words, F and G are now split apart. So effectively, whatever F and G is shorting becomes unshorted. Why does it do that? Well, when you activate off, F and G closes. So you have to look at it the other way. Whenever any of these are on, F and G is open. The minute you activate off, F and G closes. Why is that? Well, let's look at the schematic. If you look at the schematic and we look for one F and G, it's over here. Now, when any of the radio functions are on, whether it's pickup or one of the channels, F and G are open, which means that any signal coming in from the audio goes up here and is able to pass into the audio section. The minute you activate the off switch, this happens. So any audio that's present over here gets shorted to ground. And what this does is that it immediately silences the audio amplifier, so that the minute you hit the off switch, even though the capacitors still have charge and the radio normally would still work for a few more seconds, the audio is immediately cut off. So whenever we activate any of the others, for all intents and purposes, this is open. And that's how we're going to leave it for now, so we don't have to worry about that anymore. Now let's go one step further and let's look at the pickup circuit. What happens when you hit pickup? Now what I want to do in this video is I want to follow the signal with the logic of these switches and see where they activate and what effect they have. But I also want to show you what some of the tone conditioning circuit does, which means we're also going to look at the bass treble switch and the jazz and orchestra switch. When we come to that in the circuit, I'll stop and we'll come back and see what happens when these are activated. And I also want to show you on the screen here, using the Visual Analyser program, I want to show you what these signals look like and what the effect of the tone shaping is as it goes through the circuit. So stick around, it might be interesting. What I've done is I've drawn the switches and the positions they are in the off position with these red marks over here. Now we'll follow this through and I'll show you the logic. If we look at the pickup, which is input here, the signal starts there goes there, and it arrives at this point and it stops because this thing is open. So you've plugged in a signal and you hear nothing. At the moment, you hear nothing because the radio is off. And when it's off, you notice that this switch here is in the wrong position. In other words, you need this little guy to come down in order to bridge the gap. On the switch itself, this is it over here. It's 3HIK. 3HIK. Now, when you activate pickup, all these move up. Everything moves up in the switch direction, and now you've got these activated, which means you've just connected H and I. So you've made that contact. You've also activated column 4, and on column 4, what you've done is you've closed D and E, and you've opened K and L. Now 4, D and E is this guy over here, so that's just been closed, and you've also opened this one. So what have you done here? Well, if we start with this one, that's quite easy. What we've done is we've just taken the supply from the EM84 Magic Eye tube. The logic is you're playing gramophone, you don't need the supply, you don't need the Magic Eye tube at all. So that's switched off. The other effect on here is a tone shaping effect, which we'll see when we get to it. But right here, we've also done something important. We have opened the path for the signal, because the signal can now go through here, and it has to go there. So you've allowed the signal to go one step further. Now here there are two branches. This one down here, 2.2 meg, this is a record out. So we won't worry about that. You put a tape recorder in there, whatever audio is coming through gets recorded. That doesn't really interest us. What interests us is what goes on a little bit further ahead. And this is what happens. It goes through that capacitor. It goes to here. It can't go left because that's been opened. And it gets to this point over here. And when it gets to this point over here, it starts seeing options. And audio loves options. The options here are as follows. Mr. Bass looks down and says, hey, I can't get through that. That's a capacitor. So I've got to go through here. So bass goes through there. But not only does bass go through there, but treble goes through there as well. But treble, because it's a higher frequency, sees this capacitor and says, I can actually go down there. So it comes down here. And what does it find when it comes down here? Well, it actually finds a resistor to ground. And treble seeing a resistor to ground is a bit of a dead end, because what it does is it actually bleeds to ground. Not much, because this is a 5 meg resistor, but some of it does bleed to ground. Now, depending on where this pot is, there's an escape route, because part of it will definitely bleed to ground, a very small amount, but if this pot is near the top, it then finds an alternative path, and Mr. Treble can now do this. So the high frequencies have found two paths, one straight through with the bass and another one to here, because it's a high frequency path. Now what it does here now is it can actually join the bass over there. So what we've done here is we've allowed more treble or less treble to go through. We've adjusted the amount of treble that can go through. And the range will be from when this pot is at its maximum. In other words, the path is straight through to there. We've made it easy for the trebles to get through to that part. And the alternative is when this pot is all the way down to ground, to the minimum, and it's just going to see a small, very tight little path to ground, and none of it gets through to that side, because that side will also be at ground. Okay? And when that side is at ground, this path here becomes a two-way street, because the treble that gets through when this is set high joins the treble that's up there already. But if this is down at the bottom, part of that got through also leaks to ground, which is not a good thing. So this is your treble control. And the amount of range that we can get on this treble control, we can actually test with that audio analyzer by running a sweep through the amp and getting two traces, one with the treble on max and one with the treble on minimum. So let's see what that looks like. So this is the setup. The radio's got the pickup selected. The output is going to the scope, monitoring the speaker output through the dummy load, where I can activate speaker or dummy if I don't want the noise. I've got the signal generator, which is going to produce whichever sweep I want. Most of them will be from 20 Hz to 20 kHz. The output from the speaker is also being monitored by the Visual Analyser software. I've got the output from the speaker going into the sound card. It's going through a potentiometer just so that I can adjust the maximum range. And the software is Visual Analyser 2019, which is not a fantastic bit of software, but it does give us a little bit of an indication of what sort of frequency response we get because it has the spectrum analyzer function. I'm not really using the scope function on it. I'm also not using the signal generator function on it because I can program that to do the sweeps. Now the first sweep I'm going to do is going to serve as a normalization sweep. And the reason for that is on this sweep I'm having treble on maximum, bass on maximum. This thing is set to treble, in other words not activated, and this one is set to orchestra, in other words not activated. So that'll give us a baseline from which against which we can compare all the other sweeps. All the sweeps I'm going to do will be from 50 Hz to 20 kHz. They are logarithmic. And I'm doing 10-second sweeps. The longer the sweep, the more detail you can get, but 10 seconds with a few repeats seems to have worked pretty well for me. And so that's what I use. The reason I start at 50 Hz rather than 20 is that this software at low frequencies is very inaccurate and we get very few plot points, so I'm not even bothering with anything below 50. And also at 50 we have a hump, which is hum picked up by all the wires hanging around here. So I don't really look at this for accuracy, I look at this for tendency. So first of all, I'll set the peak hold function on the spectrum analyzer and start the sweep. Okay, what we see here is a pretty flat response. All the way up here, starts dipping somewhat. At 1 kHz, you've got this slight dip. It rises just a little bit, and then there's a sort of linear drop all the way down to the 20 kHz mark where it dips sharply. That sharp dip is more to do with the sound card than anything else. So this is our standard sweep with all the controls on max, and with the piano keys selected for treble on the left one and orchestra on the right. Now here's the sweep for treble on minimum, everything else staying the same. Pretty obvious response. It starts cutting off a lot earlier, about 200 to 300 Hz, and then it just keeps going down, 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 down. Down here you're way at the bottom, even before 10 kHz. You're on 8 kHz here, and then it sort of flattens out, and of course you've got the final roll-off at 20K. So, pretty dramatic range for the treble pot. In fact, on this control you probably won't hear much. It's going to be so bassy that it's going to be rather unpleasant. Now if we continue our path, we were over here, and whatever sound has got through, whatever frequencies have got through, have got to carry on, right? So they get to this point, and they see a capacitor and a variable resistor. So what happens? Well, high frequencies shoot through. High frequencies love capacitors. So they shoot through and they get to the top of the pot there. Bass frequencies get a bit stumbled here, but they have a path. They've actually got a resistor over here, and they can get through. However, the amount of bass frequencies that get through depends on the setting of this bass pot, and it's wired as a variable resistor. So if this bass pot is all the way to the left, the bass frequencies have a very high resistance to go through, so less bass frequencies get through. If it's all the way to the right, then it's just a short circuit, so all the frequencies that are in the bass range that are over here get through, and they go to the top of the volume pot, which effectively is quite close to home. But let's see what the effect is on the Visual Analyzer. Now that first one we saw, that standardization curve, was with bass on maximum. Now I'm going to do one for bass on minimum. And obviously you get the cut at the bottom. It starts cutting from about 400-500 Hertz down, and you can definitely see that cut on the bass frequencies. So that was bass on minimum. Okay, carrying on with the adventure. Our signal has now got to the top of the volume pot. So what happens next? Well, usually when your signal gets to the top of the volume pot, and the bottom of the volume pot is connected to ground, as this one is, the only thing you have is a potential divider. So the wiper takes off a proportion of that signal and sends it off through that capacitor to your amplification circuits. However, these guys didn't want to leave well enough alone. You had to get something else in here. And what they have in here are, I believe they call it psychological volume, something like that. It's got something to do with that. And what it basically means is that from the volume pot, on various parts of the taper of the volume pot, you have offshoots, you have tags coming out, and you can add circuits to those tags. Now, when we look at this one here, for example, I'm just going to give a figure. This is 0 ohms. The total pot is 2 meg, 2000 kilo ohms. At the bottom is 0. Let us say that at 10% of this, so at 200 kilo ohms over there, there's a taper coming off. Now that means that when the wiper is on that taper, it becomes a parallel circuit to whatever is connected to that tag. In other words, if your wiper is rotated clockwise to 200 kilohertz, what do you see? What does the audio see? Well, the audio will see two paths. It's going to come down here to 200 kilohertz, and it's got two choices. It can either go up there, and it does, or it can also escape through here. Now, where would it want to go? Well, you'd think it would want to go through the capacitor, but don't forget that capacitor is also a resistor to some frequencies. So some of it literally gets driven off, gets tapered off, but there are frequencies that come down here. Now, which ones come down here? Well, you've got high and low frequencies looking for a path. They get here, they find a resistor that affects them both equally. So they both go through, or some of them go through. Then they get to here and they say, "Ooh, wait a minute, that's a capacitor." That capacitor for low frequencies is an open circuit, so low frequencies don't want to go down there, but high frequencies do. So what do low frequencies do? What do the others do? High frequencies, some of them, in fact, get leaked to ground. So that's a leak to ground for high frequencies, or some high frequencies. They also try to come through here, and they get to there, they find a resistor. Yep, I can get through that. And then they find, whoops, there's an open circuit. So we got to go back, and that's it. That's what happens when it gets to that point there on the volume control. Some of the high frequencies get shunted to ground. And the effect is that the tone, or the part of the sound that gets through to the amplification stage, is warmer. I suppose you could call it that. It's got less sharpness to it. So it becomes sort of psychologically louder. I think that's the idea. My explanation might be a bit weird, okay? There's also another point when the volume is higher up here. So sound has come in and it finds the same situation over here. Now over here you've got an even more complicated situation. You've got a capacitor that allows leakage to and from that point. Now usually it'll be from that point, but it also has a path that's sort of looking for ground, and it goes through here and it gets to this point. And then what happens? Well, it depends on what this selection is. If this selection is TA, which has been activated, then it misses this resistor altogether. So it'll go through the path of least resistance, and it gets to here, and the base frequencies say, whoa, we don't need this, we can't handle this, so only higher frequencies leak to ground. So again, this is a leakage path for some higher frequencies. If that switch, that red one, was not activated, as it won't be on some selections, we've got another option here where it is activated, and 5, I believe, is long wave. Then what you've got is you've got a higher resistor to go through. It's gone through 180K. It has to go through 330K as well. And it says, whoa, geez, this, not many can work up the motivation to leak to ground in that regard, in that case. So a lot of it will go back into here. And that's what we've got. We've now got the signal coming in here and goes straight to the grid of the first preamplification stage, or the first booster stage. This actually acts as an amplification stage. It's a triode cathode biased amplifier, and that's the first one that gets sent to your power stage. Now, once it gets sent to your power stage, there are no more selections here. The signal basically, as I've explained before, gets amplified here, goes up, goes through that capacitor, goes into the grid of that power tube, which in turn boosts it and pumps it through the primary of the output transformer. Part of the signal comes down here, goes into that, and because this is another triode amplifier, it inverts it, and the inverted version of that original signal comes out, goes through there, and goes into the grid of that power tube, which in turn drives the output, and that's where you have the push-pull. So I'm not going to focus too much on this. I'm actually more interested in all the switching, as I said originally. And now we have the two clang switches, okay? Now the clang switches, the left one is bass or treble, and the right one is orchestra or jazz. Now let's look at that on the switching diagram. And what we're going to focus on now are these two. This switch over here and that switch over there. And what we see here is when this button is not pushed, in other words, we know from looking at it and from having experimented with it, that if it's not pushed, then treble is selected. When it is pushed, bass is selected, and what happens is these two swap over. So when you push this button, this is what happens. That's now with bass activated. So it breaks 5 and 6, and it makes 4 and 5. It breaks 11 and 12, and it makes 10 and 11. We're going to look at the bass, and we'll get back to the jazz orchestra in a second. Let's go back to the schematic. Looking at the schematic, there are exactly two instances where this bass and treble switch activates. One of them is down here, and the other one is over here. So let's look at this one here first. When we look at this part of the circuit here, in its basic condition, in other words, with treble activated, that's when the switch is not pressed in, then what you have here is the treble frequencies that come down here and leak to ground, which is the explanation I gave you earlier with that switch open. With treble activated, you now have another path. So your bass frequencies can escape as well, and they escape through here. They leak to ground, which means that because this is in the treble position, remember, the resting position, Bass leaks, therefore less bass gets through, therefore the sound is apparently a higher frequency, more treble, okay? If you activate this switch, that means you want bass. Then this is what happens. The switch opens. So all the bass frequencies that were escaping to ground through that 47K resistor no longer escape. The only way they can get through is into the amplification circuit, so your sound is more bassy. Now what happens on this side? Putting these two switches back into the treble position, remember, resting, they're both made. What happens here is this particular switch is on the feedback circuit, and it brings in or cuts out or bypasses a capacitor. In other words, what it's doing is it is doing something to the bass frequencies. If this switch is open, the bass frequencies can't get through the capacitor. If it's closed, all frequencies get through the capacitor. So if you bear that in mind, then what you've got here is a feedback circuit from the speaker. It comes down here, all frequencies come down here. They go through that resistor. We won't worry about the leakage to the bottom yet, but we will have leakage. But it goes through that resistor. And what does it see? Oh, there's a switch here. I don't have to go through the capacitor. Brilliant. So all frequencies go through there and they get to here. Now because they've got to here into the cathode of this amplification stage, all frequencies, that means that bass also gets to here and also subtracts from that signal coming in. So a little bit of your output is being subtracted from here. It's negative feedback, okay? Which means that a little bit of all the frequencies get taken out of there. So the trebly high frequency sound that you've established over here gets through and gets amplified. Now what happens if you do the opposite? If you open the two switches, that's what you've got. Now you've selected bass. You want more bass. Now we've determined here that when you want more bass, you stop bass leaking to ground while letting high frequencies leak to ground. What happens here? Well, the signal comes back, full range, gets through that resistor, through there, through there, through there, and then it meets a stumbling block. It meets a capacitor. Now bass says, wait a minute, I can't fit through there. But treble says, yeah, I can. So treble shoots ahead, leaving bass behind. So treble feeds back to here and subtracts treble from that signal, which is then amplified. The difference is amplified. So whatever signal you've got in here, minus some treble frequencies, is what's getting amplified and eventually gets through your speaker, which means you've made it more bassy, and that's what you wanted, okay? It's exactly what you wanted. And that's how the bass treble switch affects the circuit. And now, having selected the bass button on the left piano key, let's see what we get. And here we go. An obvious hump on the bass frequencies, the rest staying more or less the same as the standard. But you definitely see a big hump here. Bear in mind the resolution in this part of the spectrum is very poor, but it does give us an indication of what we're getting there. Coming back to the switching, if we want to activate the orchestra and jazz switch, in its resting position, it's on orchestra. And the only switch here is this one here. It shifts from keeping 11 and 12 closed to making 10 and 11 closed. So the only thing that happens when you activate jazz is this. So you've now opened 11 and 12, closed 10 and 11, and you've now selected jazz. Looking at the schematic, we only find one instance where the orchestra jazz switch activates, and that is this point down here. In the orchestra position, it's open. In the jazz position, it is closed. So let's see how that affects the audio. We've seen before that you have a negative feedback circuit. These are all signals that want to be subtracted from the signal that's eventually going to come out again. So they all come here and they get to this point, and we've seen what happens when it goes through there and the effect of the bass treble switch. However, what happens here? Well, here we see a capacitor. So bass frequencies can't get through there, so they don't go anywhere. This does not affect the low end of the signal. However, high end gets through. How much high end gets through depends on how much resistance it finds from this point to ground. Now, in the position that it's in, it finds a 1.8K resistor to ground. So some treble gets lost, but not too much. In other words, a lot of treble, or quite a bit of treble, gets deducted from here, because most of the treble actually goes straight through and gets deducted from the signal. What happens if you activate the jazz orchestra switch? Now you've got that. Now this signal over here, that was finding a difficult path to ground, suddenly has a very easy path to ground. Boom. And a lot of the treble content of this feedback signal simply gets shunted to ground. 150 nanofarads, 0.15 microfarads, is actually quite a big capacitor. It allows quite a lot of high frequencies and even some mid-range frequencies to get through. In other words, you are leaking all those frequencies to ground so that they are not available to go and get subtracted from your input signal. And that's the effect of the orchestra jazz switch. Alright, now with everything else standardized, the left piano key selection is back to the treble setting, which was the flattest setting. And now the one on the right, I've selected jazz. Et voila! One big treble hump on the 2 kHz range. That gives us the jazz setting, and then it starts cutting off down here. So that is our jazz setting. It certainly accentuates the treble frequencies. There's one thing to bear in mind when you look at these settings: jazz and orchestra, bass and treble. Whichever setting you have on here, you can get a different combination as well, because you can put this on bass and this on jazz, and that'll give you a big mid-range dip. You can play with this any way you like, and if you were to do curves or traces, they'd be endless. But the other thing to realize is whatever you select here, you've still got the full freedom of adjusting your treble and your bass tone controls. So this thing is pretty flexible as to the tones that you actually get out of it. The other thing to bear in mind is that depending on where your volume control is, the actual frequency response changes. Because that pot has got those fixed resistors coming off various parts of the taper, and the idea is there is to give you sort of a psychological loudness control. That also affects it, because depending on where you are on the volume control, you've got those circuits affecting the tone as well. So all these curves you've got to take with a grain of salt, because they do give you an indication, but they do not give you absolute values. But it's pretty interesting just how flexible these guys have made the tonal circuits. It's incredible. It's infinite, the number of options you can get, all because of the 4 controls and also the effect of the volume control setting. So that is our tonal network. Well, folks, I want to thank those of you that are still awake. I'm nearly not one of them. That is a little bit long-winded, I know, but I sometimes do these things so that I can get into my own head, and I decide to punish some other people with my thinking as well. I want to thank you if you've been watching, and if you like it, please click like, subscribe, share, and all that jazz. And also let me know if you want me to do put you to sleep with descriptions like this of the remainder of the circuitry. There's a lot of material. Thanks for watching, and I'll be back soon. Bye for now.